Okay, let's start the class. Hi guys, welcome to NEET World Institute and NEET World YouTube channel. So in this class we are going to concentrate on this EAPCET, that is fluids, mechanical properties of fluids. So in last class we were studying about the continuity, like equation of continuity, right? Like AV is equals to a constant. So the next one is like area and velocity. Okay, like area and velocity is always is constant. That's the thing we were studying in the last class, right now. So A into V is always constant, like whatever the velocity of the water going in that particular area A1, whatever the velocity of water coming out V2, this is A2, let me take, okay. So A1 V1 will be equals to A2 V2. This is the thing we were studying in the last class, that is equation of continuity. Okay, so the next one is a turbulent flow. We will see what is the meaning of turbulent flow and where it occurs. Okay, so steady flow is achieved at a low flow speed, obviously, right? When I talk about a steady flow, no, it achieved at low speed. When fluid is going with a low speed or less speed, we can get the steady flow. So beyond the critical low speed, this flow loses steadiness. Beyond the critical, like the point from here, the beyond the critical low speed, the flow of the liquid loses the steadiness, okay, and it becomes turbulent. So what is the meaning of the turbulent flow? So irregular, like irregular or disorderly flow, okay, disorder flow or irregular flow of a liquid is known as turbulent flow. Okay, so this is the basic idea about the turbulent flow. Got it? Yeah, you can take a note of this and we can go for the next one. Done? Okay, so the next one is a Bernoulli's principle. So it is the one of the important topic when we talk in JEE point of view, EAPCET point of view or NEET point of view, like any entrance examination. This is one of the important application, important topic in the fluid, like, okay. So in a fluid of, in the flow of fluid, the sum of pressure, okay, in the flow of fluid, sum of pressure, kinetic energy and then potential energy, okay, remains constant, which means pressure plus kinetic energy plus potential energy is always constant, right? So this is the Bernoulli's principles tells. So P plus of rho V, okay. Why we have taken rho V instead of mv square? Because we are talking about the density of the liquid, okay, and plus rho GH, okay. So of rho V square and rho GH, okay. So this is will be always constant. This equation is always constant, okay. So how I can take for this a simple pipe, right? So P1 plus of rho V1 square plus rho GH1 will be equals to P2 plus of rho V2 square plus rho GH2, okay. So this is how we will write the equation for the Bernoulli's principle, right? Got it? Done. Okay. Yeah. So here we'll see what this principle says, like what is the work done. Okay. So work done by the fluid at the left end, like when I talk about in the left end and the right end, no. So the work done, if you see here, it is P1 A1 into V1 delta T. Okay. Like simple in terms of P and V, it is P1 delta V. Okay. And since the same volume passes through the both region, from the equation of continuity, no, the work done on the fluid at the other end also P2 delta V. Okay, like same volume, right? That's why we have taken P1 delta V and P2 delta V. Okay, so what is the work done? Like work done is nothing but pressure into volume, right? Pressure into volume. That's the thing we have talked, and we will talk this thing about in the thermal properties and thermodynamics. Okay, like that combined lesson we will study about what is the work done of that, right? And work done on the fluid is minus P2 delta V on the fluid. Okay, so total work done will be W1 minus W2, like which is nothing but delta W, which is nothing but delta P into delta V. So V is common, like P is nothing but delta P is nothing but P1 minus P2. So part of this work goes into changing kinetic energy of a fluid and parts into changing gravitational potential energy also. Like some of the work done will be in the form of kinetic energy and in the form of gravitational potential energy too. Okay, this is about the work done of the Bernoulli's principle. Done. Can we go for the next one? Okay. So if the density of a fluid is rho and its mass is delta m, right? So how I can write in terms of density and the volume, it is rho into delta V. So the mass passing through the pipe in the time delta t, how I can take it is change in gravitational potential energy, that is delta U. Like volume is Same, gravitational is same, density is also same, no, only height will varies here, height is varies here. So the kinetic energy also half into rho v, rho delta v into v2 square minus v1 square. So from the work energy theorem, no, what is work energy theorem? Like change in kinetic energy, we will say, no, like work done will be equals to change in kinetic energy, so which is nothing but k2 minus k1. So when I talk about k2 and k1, no, yeah, so if you see here work energy theorem, like work done will be equals to the sum of potential energy and kinetic energy, also we can say, like this is kinetic energy and this is potential energy. So we now divide the term delta v in both sides. What happens? The delta v goes, delta v, then delta v goes. Now what is the remaining thing? Pressure P1 minus P2 will be equals to half into rho V2 square minus V1 square plus rho G into H2 minus H1. When I take this pressure to other side, no, when I take this pressure to the other side, it becomes, yes, so P is P1 plus half rho V1 square plus rho G1 equals to P2 plus half rho V2 square plus rho GH. This is the thing we were seen in the before slide, like P1 plus half rho V1 square plus rho GH1 will be equals to P2 plus half rho V2 square plus rho GH2, right? So this is the equation we have solved before only, we have got that before only. So this is Bernoulli's equation. So what we know, pressure, kinetic energy and potential energy is always constant, like the sum of pressure plus kinetic energy plus potential energy is always constant. So when a fluid is at rest, when a fluid is at rest in the sense, like kinetic energy will become zero. When fluid is at rest, kinetic energy becomes zero. So when kinetic energy becomes zero means, like why it becomes zero? Because there is no velocity, velocity is zero, it's not flowing, right? Like there is no motion of the fluid. So if there is no motion, velocity is not there, right? So Ke is equals to half rho v square. When I talk about half into density will be there, but this is 0 square, multiplied by 0, it is 0 only. So we will get kinetic energy as 0. So what will be the equation? P1 plus rho g h1 will be equals to P2 plus rho g h2. Okay. Done? Okay. So the next one is like important points about the Bernoulli's principle. So Bernoulli's equation ideally applicable for non-viscous fluid. Okay, it's applicable for non-viscous fluid. Fluid must be incompressible. It should be incompressible, and as elastic energy of the fluid is also not take as the consideration. Okay, and it also does not hold for non-steady as turbulent flow. Whenever they are mentioning in the equation it's a turbulent flow or a non-steady, okay, non-steady flow, I can not use the Bernoulli's principle. Okay, these are the important points where you can find the particular words in the equation, so that we can directly correlate with the Bernoulli's principle. Okay, so ideally applicable for non-viscous fluid. Okay, and it is fluid must be incompressible and the elastic energy of a fluid not to be considered, and it also does not hold the non-steady and turbulent flow. Okay, so this is one of the important point. Like, yeah, it is important point only, like when we talk about in terms of question, like in they will mention words no, so these are the important words, so you should correlate with. Done. Can we go for the next one? Okay guys, so yeah, now it is application of Bernoulli's principle. Okay, speed of efflux or torsionally law we will say. So a speed of efflux from an open tank is equal to the speed of free falling body. What is the free falling body? We were studying in the motion in a straight line, no, or motion in a plane, we were like kinematic parts we were talking right now. So free falling body in the sense we were discussing about how a object has been taken when we are talking about a free falling condition. So free falling condition means object will be going towards down and initial velocity will be 0, gravitational, that is acceleration is gravitation, that is plus g, right now towards g, towards down, and this is the height. Right now this is the height. When I talk about in terms of equations in the sense of v is equals to u plus at and v square minus u square is equals to 2as, s is equals to ut plus half at square, right now. So when I talk about the first equation means I can find what is the velocity when it reaches the bottom point, like the ground, right now. So u is 0 plus g is a is g and t I can write as it is, v equals to gt. So it is in terms of gravity and time. Then what is in terms of height? Height in the sense if they mention height, the second equation I can use, v square minus 0 square will be equals to 2gh. So this is 0, I can leave as it is, v is equals to root over 2gh. Why I am explaining this thing is because whatever thing we have discussed in the free falling, no, that one we are correlating with that topic, okay. And the next one I will simply write that equation, h is equals to 0 into t plus half into gt square, how much time it has been taken. If I want, I can use this equation, h is equals to gt square by 2 where t is equals to root over 2h by g. This is time, this is velocity in terms of h and this is velocity in terms of time. Got it? I can substitute the values. So time we can take here, no, so g root over 2h by g, I can take the g inside, what happens here, root over 2gh, I am getting the same thing. Got it? So now we will see that equations, right. So if you see here, speed of efflux from an open tank is equal to free falling body, the speed of a free falling body. What is the speed we've got there? V is equals to root over 2gh, V is equals to root over 2gh. Efflux means fluid outflow, okay, the meaning of efflux, how much, like a fluid going out, the flow of fluid is going out, okay. Now what are the terms which we are going to use here is rho, which is nothing but density, A1 is nothing but area of cross sectional of area of cross sectional of the hole, and A2 is nothing but cross sectional area of the tank, the whole tank we are talking as a A2, the small part of the whole we have taken, no, that is A1, and the pressure of the air is P2 we have taken, pressure of the air. If you see pressure of the air like in here, and this one is pressure, which pressure? Atmospheric pressure. So Y1 and Y2, height of the hole from the bottom, Y1 and Y2 is nothing but height of the free surface of a liquid, free surface. Okay, got it. So from the equation of continuity, A1 V1 will be equals to A2 V2, right. So V2 will be A1 by A2 into V1, got it. So if you see here, A2 is always greater than A1, no, A2 is always greater than A1, right. And what about V2? Yes, it's 0. So when we substitute the value, yeah, because why it is 0 means A2 is always greater than A1, no. So it's approximately equals to 0 we will take velocity, got it. Sir, when do you say ray optics? So once I complete this 11th chapter, we will start with the 12 chapters, okay. Okay. So now if you see the height which we have got, I mean the velocity which we have got here, no, in the previous case, the free falling body, what is the velocity we got here? It is V is equals to root over 2gh. So the same comparison which we are going to take in the speed of reflex also, okay, the same velocity, it's equal to free falling body, right. So what we have got here, V is equals to root over 2gh as the value, okay, this is the velocity, got it. Yeah, no need to talk about this derivation. So like when we talk about the free falling body condition with the speed of reflex, no, we will get the velocity, velocity is equals to root over 2gh. Yeah, once you can see this conditions. Got it? Yeah, now you can see this, now you can take this velocities now. Okay, now you can correlate with that speed of flux with free falling body, right? Okay. Yeah, we have used the condition Bernoulli's theorem here. So by using Bernoulli's theorem, we got this velocity, right? So when we are talking about that correlation with the free falling body, we got the same velocity. Okay, that's why I have taken a correlation with that free falling body too. Done. Okay, so the next one is a venturimeter. It's a device to measure flow of speed of incompressible fluid, flow speed of incompressible fluid. So from the equation of continuity, you know, like A1 V1 will be equals to A2 V2, right? So we can find the outflow velocity, V2 is equals to A by A into V1. So when we apply the Bernoulli's condition, now here what is the thing is, we are considering the height, same height. So if we consider same height, potential energy will get cancelled, right? So only pressure will be there, kinetic energy will be there. Got it? Pressure and kinetic energy will be there. So we have taken V2 in terms of V1 only, V2 in terms of V1, and when we substitute that equation, we will get the term as V1 is equals to root over 2 rho GH by rho, like this rho and this rho is separate, okay, and I will tell you about that, and A by A whole square minus 1 by, so minus 1 power minus 1 by 2, okay, this one in the denominator it will come. Yeah, you can take a note of this and we can go for the next one. So rho m is nothing but it's the density of the liquid in like the tube, and rho is nothing but density of the air. Okay, it's a density of a liquid in the tube which we have considered, and this is the density of the air. Got it? So here is the question. The flow of blood in a large artery of a anthropoid dog is diverted through a venturi meter. The wider part of the meter has a cross-sectional area equal to that of artery, that A is equals to 8 millimeter square. The narrow part as area as 4 millimeter square. The pressure drop in the artery is 24 Pascal. What is the speed of the blood in the artery? Okay, there is a solid 2 minutes time for this question to solve. Yeah, give the answer for this question and we'll discuss the answers. Okay. Yeah, last 1 minute. Yeah, so now we can see the answer. The answer is V is equals to, that is velocity is equals to 0.123 meter per second. Okay, yeah, you can take a note of this. This is the answer for this question, right? Done. Okay, so next one is, yeah, the next question. So we have a solid 2 minutes for this question too. A fully loaded Boeing aircraft has a mass 3.3 kg, 3.3 into 10 power 5 kg. Its total wing area is 500 meters square. It is in the level flight with a speed of 960 km per hour. Convert it into meter per second. Okay, meter per second you need to convert. Estimate the pressure difference between the lower and upper surface of the wing. That's the first question. Second question is, estimate the fractional increase in the speed of the air on the upper surface of the wing, which is relative to the lower surface, and the density of the air is given, that is 1.2 kg per meter cube. Okay, so there is only 2 minutes time for this question. You can give answer in the comment boxes, and you can give answers whoever present in online classes also. First, last 30 seconds. Last 30 seconds. Yeah, now we'll discuss the answer for this question. So if you see upward force, which is nothing but it's a weight, no, it's equals to weight, right? Force, no, like pressure is equals to force by area. I can write force in terms of pressure into area, right? So pressure into area, and the weight is nothing but it is mg, mass into gravity. So I don't know the pressure, I'll keep the pressure as it is. I know the remaining terms. I know gravity, I know mass, I know the area. Area is also given 500 meter square, and mass is 3.3 into 10 power 5 kg, and the gravity 9.8, right? So when I do the calculation, we will get the pressure as 6.5 into 10 power 3 Newton per meter square. Okay, estimate the pressure difference between the lower and the upper surface of the wing, right now. So this is about the pressure. Next, what is the thing we need to calculate? The second part of the question. So estimate the fractional increase. Estimate the fractional increase in the speed of the air on the upper surface of the wing relative to the lower surface. So how much density they have given? It is rho is equals to 1.2 kg per meter cube, right? So when I use the Bernoulli's equation, pressure plus kinetic energy plus potential energy is always constant, right? So P1 plus rho GH1 plus of rho V1 square will be equals to P2 plus of rho GH2 plus of rho V2 square. Here height difference is ignored because it's going in the same height. So I can ignore these two things. So P1 and P2, I know the pressure difference. What is the pressure difference we got in the previous case? Yes, we got the pressure difference, and rho into V2 minus V1 into V average. Right now we can take this as in terms of A square minus B square, which is nothing but A minus B into A plus B. What is A plus B? Yes, A plus B, but this 2 I am combining with this. So A plus B divided by 2, it's the average of these two velocities. Okay, so V average is nothing but how much they have given, 960 km per hour. When we convert it into meter per second, it is 267. Okay, 267. And V2 minus V1 will be equals to delta P by rho into V average. Got it? So when I talk about V2 minus V1 by V average, we will get 0.08 approximately. Got it? So this is the answer for the second part of the equation. Okay. So next we will go for the next topic, that is viscosity. We will see. Okay. Yeah, you can take a note of this, and we can go for the next topic. Completed? Can we go for the next one? Okay. So the next topic is viscosity. So it's a property, okay, of a liquid by which it opposes the relative motion. Okay, the main important point is opposes the relative motion between the different layers. So thin liquid like water or alcohol, if we take, it is less viscous, and if we take a thick liquid, blood, glycerine, those kind of things, it's a more viscous, like high viscous. Okay, these are the a basic example of less viscous and high viscous. So water, alcohol, blood and glycerin. Okay, so it is oppose the relative motion between the layers of the liquid. Okay, that's the meaning of viscosity. That is the meaning of viscosity. Got it? So laminar flow, turbulent flow we have seen. What is the laminar flow? The layer of liquid in contact with the top surface. Okay, the layer of liquid in contact with the top surface moves with the velocity v. So if I talk about any liquid right now, like it's going with some velocity. Okay, this liquid and this liquid is contact, like the second layer of the liquid is contact with the first layer of the liquid, which is going with some velocity v. The layer of a liquid in contact with the fixed surface is stationary. Fixed surface is stationary. Fixed surface in the sense there will be a surface, it will be always stationary. The velocity of a layer increases uniformly from the bottom of the top layer. It will be increases. The velocity keeps on increases. Got it? From the top low surface to the high surface. For any layer of liquid, its upper layer pulls it forward while the lower layer pulls it backward. When going front, it will be a backward, like when we observe the thing. Okay, so this type of flow is known as a laminar flow. Got it? Yes, like we can observe, like when it's going with this speed v1 or like let me take 5 meter per second, the second layer will be like 4.8, like it's trying to oppose, no, because of that keeps on reducing the velocity. Okay, from the top to bottom, or when we talk about from bottom to top, it keeps on increasing the velocity. So this is the laminar flow we will say. Done? Okay. The next one is coefficient of viscosity. It is denoted by the symbol eta. So it is nothing but shaving stress to shaving strain. That's the thing we have discussed in the viscosity, like eta, no? Yes. So shear strain is nothing but delta x by L. So how much delta x it has been displaced in the parallel, okay, and L is nothing but the breadth, okay, and strain is nothing but strain rate is nothing but delta x by L into x into delta t. Got it? So what is the thing here? T, I mean when I talk about x, no, it is v into t. What is velocity? It is displacement by time. What is displacement? Velocity into time, right? I can substitute in terms of velocity into time. So time and time will get cancelled. It is v by L. Okay. So it is delta x by L into delta t. L into delta t. Okay. It is not x, Lx delta t. It is L into delta t. So I can rewrite this one delta x divided by L delta t. So I can rewrite this delta x as v into delta t divided by L into delta t. So delta t will get cancelled, v by L, that velocity by length. Okay. So eta is nothing but shaving stress by shaving strain. So FL by VA, like when I take this in terms of velocity and length. So force into length divided by velocity into area. Okay, so SI unit is pascals or partially will say or Newton second per meter square. Okay, so if you see, and the next thing is dimension, it is m L power minus 1 T power minus 1, and temperature increases means the coefficient of viscosity decreases. So if temperature increases, viscosity decreases, if temperature decreases, viscosity increases. This is the thing we should remember, like a question was asked in the EAPCET. Right. So when a temperature increases or decreases, what about the viscosity? It remains constant, it will increase or it will decrease, or none of this. Okay. So accordingly we need to mark the answer for this question. Got it? Done? Okay. So here is the homework question. You can do this question. A metal block of area 0.10 meter square is connected to a 0.01 kg mass. Okay, via a string that passes over an ideal pulley. Okay, a liquid with a film thickness of 0.3 mm is placed between the, this is the liquid, okay, this is the liquid film, placed between the block and the table. When released, the block moves to the right when with a constant speed of 0.085 meter per second. Find the coefficient of viscosity of the liquid. Okay, this is the homework question. And try to solve this question before coming to the next class, and we'll discuss the question in the next session. Okay, so thank you guys. With this we'll end up today's session of mechanical properties of fluid of EAPCET. Right? Yeah. Okay. Thank you.